Hi everyone, here's Ray from UC Santa Barbara. I'm happy to introduce our new work on ECCV'22, Language-Driven Artistic Style Transfer. This work is also collaborated with Eric from UC Santa Cruz. Let's first talk about artistic style transfer. I think most of you are familiar with this topic, where we want to render a photograph with a given artwork style. It has to preserve the content structure of the photograph and present the style patterns from the artwork. So the input should be a content image and a style image, and we have the stylized output image. However, we have to prepare a collection of style images in advance, and the user needs to search for the desired style they want. If there is no expected style, we first have to redraw a new reference image to fulfill the requirement. This restriction makes it impractical due to the additional overhead. On the other hand, language is the most natural way for humans to communicate. If the systems can follow textual descriptions and perform style transfer automatically, it can significantly improve accessibility and controllability. We can direct talk to AI about the desired style we want instead of exactly drawing it. And this is language-driven artistic style transfer, aka LDAST. We have the content image and the style instruction as the input, and we can also acquire the stylized output. To perform LDAST, we present Contrastive Language Visual Artist, aka CLVA. For training, we have all content images, style images, and instructions. But during inference, only contents and instructions are provided to realize LDAST. CLVA includes two components, Language Visual Artist, aka LVA, and Contrastive Reasoning, aka CR. LVA learns the latent style patterns from the instruction to stylize the content image, and CR compares contrastive pairs of content and instruction to further enhance the performance. LVA is composed of visual encoder, text encoder, and visual decoder. We follow the standard style transfer model where visual encoder is borrowed from VGG19 to extract content features and style features from an image. Text encoder extracts the instruction features, which is in the same dimension as the style features. And visual decoder is the reversed VGG with a self-attention transform to compose content and style or instruction to produce the transferred result. To learn from the pair of styles and instruction to perform LDAST, we apply the following training objectives. Firstly, we consider structure reconstruction, that the model has to reproduce the content image from the original content features and style features. Hence, the model can preserve the target structure from the content image. To learn the style semantics from the instruction, we have patch-wise style discriminator D. D distinguishes that an image patch is from the paired style image or the stylized output according to the instruction. By optimized to full D, text encoder can learn the latent features from language and make the stylized output have the similar patterns, like the style patterns, to the style image. To further enhance the alignment, we utilize content matching and style matching, where the transferred result should contain similar content features to the content images and similar style features to the instruction. Apart from the single pair of content and instruction, we also consider the contrastive pair of the same content with different instructions or different contents but with related instructions. The main concept is that the content image should transfer to various styles while preserving the same structure, and related style instructions can apply similar style patterns to arbitrary content images. For example, for consistent matching, stylized outputs from the same content C2 should have similar content features, and they should present similar style features from the same instruction X1. In addition, different style instructions, which imply corresponding visual semantics, should still present relative patterns. For example, we can only discover reach up to the sky literally from X2. But if we compare the reference style images S1 and S2, we can perceive that the sharing of similar style patterns and link the visual concept of bright tall hills in X2 to mountains looming over the lake in X1. To do this, we borrow the cosine similarity of the style image as the relatedness between X1 and X2, and this style similarity should also reflect in the stylized output. For the experiments, we collect 5,000 wallpapers, including diverse scenes, as the content image. We treat two style datasets, DTD and ArtEmis, where both contain style images and their corresponding instructions. For the evaluation, we adopt the stylized results by ADA attention using style images as the semi-ground truths to support large-scale automatic evaluation. We consider three different metrics. Perceived loss is to calculate the distance of the grain matrix from the VGG visual features between the transferred result or the target style image. A lower perceived loss shows that this stylized result presents more similar patterns with the style image. Friendship activation distance, aka FAD, is widely used for image generation, which compares the distance of the inception V3 features with the semi-ground truth. A lower FAD means the stylized result is more similar to the semi-ground truth. VLS is a relative visual text similarity from the pre-trained CLIP model. We use this to compare the alignment to the given instruction. A higher VLS is better since the stylized result is more correlated to the language. For baselines, we consider them from different aspects, including the standard style transfer, language-based image editing, and clip-based optimization. For the style transfer models, the extracted instruction features are jointly embedded with the style features, so that they can directly perform style transfer by the given language during testing. We first take a look at the DTD results, where the instructions contain visual attributes such as colors, textures, or materials. Our CLVA surpasses baseline on almost all automatic metrics, excluding Clip Styler on VLS. Since Clip Styler is directly optimized by Clip, its VLS is slightly higher than our CLVA. But CLVA still shows better performance on human evaluation. We let Mechanical Turkers rank the similarity to the content, the instruction, the style image, and the semi-ground truth. A higher ranking score shows this method is more correlated with the target aspect. From the view of visualized comparison, Clip Styler is sometimes misguided by Clip, such as the bright white background in the third case. On the other hand, CLVA can extract a more detailed style like brown metallic in the first row and stringy hairy in the third case. Similar results can be found on ArtEmis, where the instructions are more challenging emotional effects such as nightmare or charmed by the beautiful bright day. We can see that standard style transfer methods like SANet and LST contain unsmooth and fragmentary patterns with blurring contents. Again, our CLVA is competitive to Clip Styler on VLS even if without clip guided, and comprehensively superior on human evaluation. Specifically, despite not being instructed literally, our CLVA can perceive sight of the water and reveals the latent grassland precisely in the third case. For StyleClip and Nada, they relied on a pre-trained style gain from the specific content domain. So we compare them in the domain of car and church. Though they are directly optimized through Clip, our CLVA still has a higher VLS than both, and the lowest perceived loss means our stylized output can have the most similar expected style patterns. For the qualitative examples, StyleClip shows limited modifications and Nada even destroys the thing. In contrast, CLVA presents the detailed pinkish interplace clothes or the color cream precisely on the surface of the church. Let's check the ablation study. In the first row, with only structural reconstruction and patch-wise style discrimination, CLVA can have quite promising results. Content image can help the structure similarity, and style matching helps the style similarity. So you can see a lower perceived loss and a higher VLS in the third row. If we combine both, CLVA should strike a balance in between and have a lower FAD to the semi-ground truth. And finally, the contrastive reasoning leads to a comprehensive improvement, which shows that considering consistent matching and relative matching for different pairs of content instruction is crucial in LDAST. The next thing we want to investigate is why our CLVA performs better than clip-based method. We all know that clip is strong on text-visual alignment, which should provide robust signals for those methods to update. We launch a instruction to style retrieval by our learned CLVA or clip. Surprisingly, we find that CLVA is significantly better than clip on both DTD and ArtEmis. We hypothesize that clip cannot capture detailed style patterns very well. Similar results can be found in visualization examples where clip can only present bright colors or tone, but our CLVA can capture more related happy place to live. In addition, even though the clip module in Clip Styler is fine-tuned on the DTD or ArtEmis dataset, humans still think CLVA's style transfer results are better and more related to the guided instructions. Apart from the effectiveness, we also check out the efficiency of the introduced LDAST, since the original style transfer can be carried out super fast nowadays. We run on a single Titan X GPU with content image size 256 by 192. For StyleClip, Nada, and Clip Styler, those clip-based methods required numerous iterations for optimization, which occupy a huge GPU memory and may take up to 100 seconds for the transfer. At the same time, since they are updated for each given text, they can only run one input at a time. On the other hand, our CLVA only needs one step to acquire the stylized output, and it can also take advantage of parallelization to perform 50 cases in half a second. Another interesting application is linear interpolation, which is to combine two styles upon a content image. Our CLVA also supports this with two instructions. The joint interpolated style feature is a linear combination, and this can reflect on the stylized result where we can see a smooth transformation in between. In conclusion, we present a new task, language-driven artistic style transfer, to control style transfer directly through natural language instead of preparing a style image in advance. We propose contrastive language visual artist, aka CLVA. CLVA learns to extract explicit visual semantics from style descriptions to perform LDAST, and the experiments show that our CLVA can carry out instructions with visual attributes or even more complicated emotional effects. You can find more qualitative examples or give it a try from the QR code. Here's Ray from UC Santa Barbara. Thanks for all your listening about our language-driven artistic style transfer.